CITS Pre-Calc Section 1-2 is on formulas and applications. Now what they start with are just some general formulas, be it our similar triangles, business applications, things like that. We go to investment problems, uniform motion, which are usually a little more difficult with the distance, rate, and time, the mixture, and the work problems. So in general here, they've got 6 different types of problems that they have us work through in this section. Again, when we go back to a regular pre-calc class or an advanced algebra class, these types would have been worked through a number of different chapters. So if you're a little weak on that background, the book does a good job of giving some examples of each type of problem, which I've highlighted here. The problems with the similar triangles, example 4, business applications, investment, so on and so forth. So if you need to go back and look at more examples, I have some of those here. You can look at in your book. I'm doing one of each type here so that you can see it done as for an example. And then also we'll do whatever examples we need to in class. And hopefully we'll make these not as bad as they need to be. Okay. If we start out with number 28, and I'll read it to you. You can see it pretty well on the screen there, but I'll read through it. It says the height of a building. A building casts a shadow 50 feet long. A rod 4 feet tall placed near the building casts a shadow 3 inches long. Use similar triangles to determine the height of the building. Now the thing with similar triangles is that the top and the bottom of each of those ratios that we use have to be in the same units. Okay, I'm not saying the top has to be the same as the bottom, but the ratio, the top of each side and the bottom of each side have to be the same, or numerator and the denominator. So just a quick diagram to show us what we have. We have a building here. It's going to cast a shadow that's 50 meters long. Over here we have something 4 feet tall, and it's casting a shadow 3 inches. Now our general rule states that I can take the height of the building over its shadow. That's going to equal the height of the rod over its shadow, because they're both a similar triangle. Now the thing is that they have to be in the same units. So this ends up being x, because I don't know the height, over 50 feet. This ends up being 4 feet over 3 inches. Well, 3 inches we know is 1/4 of a foot. So it's actually 4 over 1/4. Okay, if I just do a little bit of quick math to it, this gives me x over 50 equals 16, which when I cross multiply or multiply both sides by 50, I get x equals 800 feet. Okay, so the building is 800 feet. I also like it when students phrase their answer. Those that you have had me before know this. Those that are new to it, I always want your answer phrased as a statement at the end of the problem. Okay, I want you to be able to explain what that answer is. So the building is 800 feet tall. Okay, number 36 out of your book is a business problem. The price of a magazine subscription rose 4% this year. If the subscription now costs $26, how much did it cost last year? Well, what we can do is we're going to let our variable equal the cost of the original subscription, the original price. Okay, now if that's the original price, I know if I'm going to have an increase, I take the original price and I add the increase, which is 4%. Again, we have to use that as a decimal. And that's going to equal the new price of the subscription. Solve it out. 1.04x equals 26. Divide both sides by 1.04 and you're going to get 25. So therefore, the subscription was $25 last year. Now I realize that these two weren't real difficult, or shouldn't be real difficult for you guys, but they do start out a little bit easier, and so I want you to make sure you pay attention to these last ones. There's actually one, number 52, is a little bit tougher. If you haven't done mixture problems, it definitely can be. So we'll start with number 40 here. Number 40 is an investment. An investment of $4,600 is made at an annual simple interest rate of 6.8%. How much additional money must be invested at an annual simple interest rate of 9% so that the total interest earned is 8% of the total investment? Okay, a lot of stuff there. Now, what we're looking at here is I always like to start out, we're looking for the amount invested at 9%. Okay, so that's what I'm going to let my variable be. Now, knowing that simple interest is figured by principal equals the rate times the time, I can set up my equations saying if I know the interest at 6.8%, and I add the interest gained at 9%, that's going to be my interest at 8%. Okay, so that's my general thinking. Interest is giving to us. We know 6.8% we can't use as a percent. So I'm going to change it to 0.068, 0.09, and 0.08. And now, so it's that times my amount, or times my rate. So what I've got here is I've invested $4,600 at 6.8%. So this is times 4,600. I invest another amount at 9%. So this is the amount I invest at 9%. And that gives me 8% of the total amount, which is 4,600 plus X. Okay, so there's our equation. Multiply 0.068 times 4,600. You get 312.8 plus 0.09x. 8% times 4,600 is 368 plus 0.08x. Divide or subtract your 0.08 from both sides, and your 312, and divide. So I would need to invest $5,520 at 9%. Again, phrase your answers. Don't be lazy. It just kind of puts a cap around the whole process. Number 47 is a uniform motion problem. Now, I like to start these out with just kind of a quick diagram, just to kind of bring our thinking around. So, uniform motion. A car is traveling at 80 kilometers per hour. It's passed by a second car going in the same direction at a constant speed. After 30 seconds, the two cars are 500 meters apart. Now, if I look at this one, I have a first car here. It's traveling along. At some point, it's passed by another car. And 30 seconds later, it's 500 meters ahead of the first car. Okay? Well, what they're giving us here is a type of problem. It's our distance, rate, and time problem. I know that the distance of car 1 and the distance of car 2 at some point are the same. But then car 2 goes ahead of them by 500 kilometers. So the first thing I have to do, I'm going to write a general equation. The distance of car 1 is equal to the distance of car 2, but it's not really, because this one has a 500 kilometer lead. So I have to subtract that to make the actual equations equal. Because this one's larger, this whole distance is, so I have to subtract that 500. Okay? So now we've got, I can break that down. Distance is my rate times my time. Now plug in what we know. Notice I haven't named a variable yet. I usually do that a little bit later in these problems, because once I start plugging in what I know, I can easier figure it out. Now there's going to be a couple of small changes here. Okay, First of all, my rate. My rate of the first vehicle is 80. Okay? My rate of the second vehicle, I don't know. But the time for both vehicles is 30 seconds. Well, notice that our rate is given in kilometers per hour. So our time has to be given in hours. Our distances have to be given in kilometers. So my time for this one is 30 seconds, which is 30 over 36 hundredths of an hour. My time for this one is 30 seconds, which is 30 over 36 hundredths of an hour. And we have this 500 meters here, which is actually incorrect because it has to be given in terms of kilometers, which is 500 over 1,000 kilometers. Okay, so the big thing about this type of problem is make sure that you put everything in the correct units. We can't do anything with it unless it's in those correct units. So just a little bit of simplification here. If I simplify 80 times 30 over 3600, I end up with 8/12, which I know isn't reduced. 30 over, this ends up being R over 120, or no, yeah, R over 120, and that's 1/2. Okay, we solve this out then. I'm going to add 1/2 to both sides. Okay, which is 6/12, so this is 14/12 then, equals R over 120. Multiply both sides by 120. Can cancel a 12 off, which gives me a 10. So therefore, the second car was going 140 kilometers an hour. And again, make sure you phrase your answer. Okay, I'm going to do 59 first. And then I'm going to come back to 52 because I see I'm at about 12 and a half minutes here. I only get 20, so I'm going to see if I can fit them both in. Number 59 is a mixture problem. It says the vendor of a coffee cart mixes coffee beans that cost $8 per pound with coffee beans that cost $4 per pound. How many pounds of each should be sold to make a 50-pound blend? Well, I'm going to let X equal one of those, the amount of the $4 beans, and I'm going to let 50 minus X equal the amount of the $8 beans. Now, if I have the mixture, I know that when I mix them, it's going to cost me $4 per pound for the $4 beans, that's 4X. It's going to cost me $8 per pound for the $8 beans, and that total value then is going to be worth $5.50 per pound for the full 50 pounds. Okay, so here's my equation. We're going to solve it out quickly. Okay, subtract, I've got negative 4X equals negative 125. So X equals 31.25 pounds. So therefore, I will mix 31.25 pounds of the $4 beans with 18.75 pounds of the $8 beans. Okay, last one, number 52. A radiator contains 6 liters of a 25% antifreeze solution. How much should be drained and replaced with pure antifreeze to produce a 33% antifreeze solution? Now, to do this problem, we have to know how to figure percent antifreeze. Well, our percents we learned years ago, but for some reason we always seem to forget them. Our percent antifreeze is the amount of antifreeze over the total solution. And that's going to be our percent antifreeze. So what I need to find out is how much antifreeze I have how much I'm going to drain, and then how much I'm going to add. So what I've got is this. I already know this part. The total solution at the end, because I'm going to drain some out and put some in, is going to be 6 liters. The total solution of antifreeze at the end is going to be a 33% solution, which is 1/3. Okay, and I'm going to use a fraction here. Now, if you use the decimal or a fraction, you're going to get a little bit of a different answer. The fraction, I think, is a little more exact, but I'll tell you that little difference here at the end. Now, here's what we got. I need to find out how much antifreeze I have. I have 25% of 6 liters. So 0.25 times 6 is 1.5. I have 1.5 liters of antifreeze already in there. That's my mixture. Now I'm going to dump some out. So X is going to be the amount dumped and added. Because it's the same amount, right? I dump it out and then I add the same exact amount to get 6 liters. How much of that is going to be antifreeze? Well, of that amount dumped out, 25% is antifreeze. So therefore, I'm going to take away 0.25x of antifreeze. Then I'm going to dump pure antifreeze in. So I'm going to add another amount of antifreeze. Okay, so the amount of antifreeze I started with, 0.25 times how much I have. 25% of that liquid is antifreeze. How much I dumped out? I dumped out X amount, a quarter of that is antifreeze. How much I added? I added X amount of pure antifreeze. So we have our equation. Now we should be able to go through and solve it out. We're going to multiply both sides by 6 first. Okay, I just combined those terms. Subtract that. And divide. Now I'm going to get 0.5 over 0.75. That should be a positive there. There's something wrong. And I'm going to end up getting 2/3 or 0.66. Okay, so I'm going to dump out 2/3 of 1 liter. Okay, I'm going to replace 2/3 of 1 liter with pure antifreeze. Now, if I were to just change this a little bit, if I were to use, instead of 1/3, 0.33, I would add 0.33 here. I would have multiplied by 6, and I would have got 1.98. Notice the difference? So coming all the way down, instead of this 0.66, I would have gotten 0.64. Now the book left it at 0.33. I changed it to 1/3, so that'll be the difference between the two answers. I prefer, if we have a repeating decimal, to use the actual fraction. I think it makes it a lot more accurate. So there's some examples of what we're looking for in this. I realize that for some of you that came through advanced algebra, a lot of these are going to be new. Okay, but you need to kind of get on them. There's a lot of examples in the book. There's a lot of problems we can work through. Just make sure you do enough so that you can understand how we work them. Okay?